I am Stephen Rudisil. I'm a R&D chemist with HP. I work on the multi-jet fusion printer. I do agent development, and I'm here to talk to you a bit about, here we go, technology and fundamentals and materials innovation. A lot of this is going to be kind of the business story, what our angle is on entering the additive manufacturing market. But then I'll get into some kind of technology comparisons and where we think what differentiates us as a technology, and discuss kind of some, in vague terms, some futures angles on what we're doing. So the way that HP sees the 3D print environment is kind of a timeline going all the way back from when we used to make goods by hand, in cottage industries. Before the Industrial Revolution, we had essentially the idea that the designer of the part was the same as the person who was making it, right? You had somebody who was knitting a sweater or something like that. And as we moved to the Industrial Revolution, suddenly those two roles got separated, right? You had designers who made parts that could be made only by specific machines. Suddenly you were able to mass produce things, but you could only make them in a specific way based on the machines that were being made. And essentially that model for production and manufacturing has carried through to today, right? We have specialized machines that make things. We have injection molders that make specific parts, and they're kind of limited by the process. It costs a lot to produce a mold, and we don't have a lot of flexibility in how we make things. The internet era has kind of improved that, so we have lots of design tools that have enhanced how people can design, but at the end of the day, we still have very specialized technology. And where we are right now is kind of in between this area, and what we would like to drive with the MJF technology introduction is move the world towards this 3D transformation, where we are making it both easier to design parts and easier to produce parts at different scales for the same price, essentially. I'll get into that in a little bit. And as we move through that kind of transformation phase, we want to move to a new industrial revolution where you have the ability to design parts and produce them is distributed to whoever wants to do it. You can get kind of the training to produce parts through systems that are generally available through the cloud, and you can get access to print technology basically anywhere you want. The idea behind the next industrial revolution is kind of a world without warehouses, one where you don't have to worry about storing goods. You can simply produce goods on the spot as demand comes in. And so part of this, whoops, is that right? Yeah, that's right. Part of this story is kind of moving analog manufacturing to digital modes, and additive manufacturing is kind of the beginning of this process. And MJF seeks to kind of expand this. And this is something that HP actually has some experience in. This kind of curve here is very similar to what we've done with our web press technology in two-dimensional printing, where you're producing large reams of printed documents, brochures, things like that. Analog presses have kind of this curve, this cost curve, where if you're producing a small number of parts, just running the machine, you never actually recoup your cost because it costs so much to actually run the machine. You can't make enough money on a small run of parts. But as you go to very large runs, the economics get better for you. The difference between what we call a digital press in this case is that the cost to produce a part, in any case, the ability to produce a unique part is pretty much fixed. And this is the case for 3D printing. If you have a line all the way across here, you have a fixed cost per amount of material, per amount of time you run the machine, and you get a fixed amount. And the goal is, as we develop our technology, right now we can produce short-run manufacturing. But we want to move this to a world where we have digital production that can compete with large-scale manufacturing processes such as injection molding. And so as we move forward and move our technology forward, we're going to be driving this analog to digital transition. We hope to move that into this 3D transformation space. There are a couple advantages that come with moving from this analog to digital transformation. I mentioned that obviously there's a fixed cost per part, makes calculations easy, I guess. But you don't get so much of the economies of scale until we drive down the cost of the technology. But the other advantage is that digital techniques for producing parts or printed media allow you to have customizability. you can produce a part that is personalized or designed to anybody's specifications, and it doesn't have to be the same every time. You know, with a mold, obviously you get the same part, and ideally you get the same piece out every time, but you can actually modify the design in a digital world and make unique parts on these large scales at the same time. And then as we go, we want the, oh, I just got loud. Sorry. And then as we move these economics to more favorable spaces, we want to produce scalable. We end up getting low risk to supply chain issues, right? We don't have to worry about storing goods. We don't have to worry about problems of parts failing in a warehouse or getting damaged during shipment. You can produce them where you want them, when you want them, and faster and with less waste. So with that, I'll kind of get into a little more discussion about the technology. So I realize a lot of people may be familiar with additive manufacturing, so bear with me. I'm going to go through a bunch of technologies here and kind of then give you a compare and contrast on what we do. So what is 3D printing or additive manufacturing? What it is essentially a general solution to manufacturing. It's a way of making parts of any shape without having to mold them or machine them. Basically, you don't have to take a large block of material and cut it into pieces, and you don't have to take, essentially rather than reducing a part to what you want or specifying the shape in advance, you can simply build it layer by layer. Most 3D printing technologies, I think all 3D printing technologies are fundamentally layer-based. So you take your design of a part, you slice it into a series of pieces, and then you use some piece of technology to produce each of those slices in sequence and end up building the part to produce what you want. So there are many different technologies here and many different materials that can be produced depending on the technique. You can produce plastics, metals, there's some ceramic printers, and they're used for all sorts of things. Parts prototyping right now is kind of the main application, but there are some end-use parts as well. There are several examples in the aerospace industry where you have parts that can be printed on a metal printer, for instance, that can't be produced any other way. And so it opens up the design space for the engineers who are designing more efficient widgets and gadgets that go into planes and trains and automobiles and so on. So to walk you through this, one of the first technologies that came out in 3D printing, I think in the 80s, was fused deposition modeling or fused filament fabrication, FDM, FFF. Essentially what that is it's hot glue guns plus robots. You essentially have a scanning axis set of stepper motors that can move a hot extruder. And what that allows you to do is basically put down a layer of material wherever you want it in an XY plane, and then you have a platform that moves up and down, or in other cases you have a motor that moves up and down that allows you to produce parts like you see here. This takes a long time. And there are some issues with layering, right? You can imagine you're putting down molten plastic at any particular place, and then that molten plastic hardens. And then when you try and put down a layer on top of it, you can't melt the previous layer necessarily. You're just kind of attaching it to the base. So one of the weaknesses here is that you get pretty bad isotropic properties. You get anisotropic properties. You get part properties that vary depending on which way you orient the part during the build. There are other methods which are based on curable resins. Essentially, this is basically doing chemistry. You're generating plastics in situ with the printer. You start with a monomer liquid, and you have a light that essentially is used to cure that liquid and turn it into a polymer in the printer itself. And so what this allows you to do is kind of use the same technology that runs your DLP projector, something that sprays light onto a surface. You're using the same thing except you're masking in UV. And so when you have a liquid pool, you expose that to a UV light and it cures wherever you put the light down. And then you have a motor or something that moves up and down and basically adjusts it so that you have exactly the layer thickness you want. The advantages here, again, are around accuracy, cosmetics, right? You only fuse the areas where the light is exposed, and our ability to deliver light is very precise. You get good surface finish out of these parts. Again, you have some mechanical property problems because you can't control molecular weight to the same degree that you'd want to in an already finished plastic. Finally, we get to some other systems that are based on lasers. This is selective laser sintering and direct metal laser sintering. Both of these are pretty much the same technology. You have a powder bed that exists here, and then you basically build layers over time. So there's a spreader system that spreads a thin layer of powder across that bed, and then you have a laser that draws across the surface. Everywhere the laser draws, the powder melts, and whether that powder is plastic or metal, it ends up being becoming the part that you want. Now, one of the advantages I did forget to mention earlier is that the SLA and FDM parts, if you have a part that has an overhang or has a complicated geometry that might tip over while you're actually making it, you have to build support layers. So SLA has to have a support material, or FDM has to have support materials that come in. Otherwise, you'll end up with parts that don't actually have the correct shape that you want. In the case of SLS and DMLS, both of these, the powder bed is the support system, right? You're basically pulling pieces out of a powder bed at the very end. And so you write on the surface, you produce your part. The advantages here, of course, you get significantly improved material properties in a lot of cases, because the laser does a pretty good job at penetrating the surface, and you can melt layers underneath. It is slow, and it's limited by the area that you build, much like FDM. If you want to fuse an area, you have to draw the laser over that surface. Contrast that with SLA, where you're actually just, some of those methods are drawing, some of them are masking. You can actually do area-based fusing in those cases. And area-based fusing is where I want to go to, because that's the main differentiator here for MJF. MJF is very similar to SLS in the sense that we have plastic powder that we're printing on. But the difference is that rather than drawing across the surface with a laser, we're printing agents, two different agents here. You can see these black drops are the fusing agent, and these blue drops are the detailing agent. And what those do is they go down and they act as thermal agents, essentially. One increases temperature, one decreases temperature. The fusing agent has a radiation absorber in the fluid, and so when we have lamps we expose the powder to these lamps, you then melt the plastic wherever you put down the fusing agent. The detailing agent can then take care of any areas where you have excessive thermal production, and they allow you to do quality part accuracy control and dimensional control. And so then we finally end up with a layer over here where we've actually fused the plastic, and the areas we don't want to be fused stay in powder form. And then we basically start the process over again. You run that several hundred times, you end up with a part that has the dimensions you want. The existing product, as I mentioned here, uses two fluids. I said the fusing agent and the detailing agent. The build materials that we have right now are PA12. Some of the things that are in the pipeline are PA11, some elastomer materials, some filled nylons. I'll get to the kind of roadmap, but I can't be specific about any particular timings on those materials. Right now what exists is PA12. So the pitch for these printers is that it allows you to prototype and produce functional parts, quality output at very high speed, and speed that is not dependent on the build area that you put in. Each layer is always the same, because you essentially have a fixed time for the amount of printing that you do. You print, you fuse, you're done. And it doesn't vary. So we get high-quality parts, as I mentioned, the breakthrough speed, and then we're moving towards lower cost per part by taking advantage of economies of scale, and some topics I'll get into in just a second here. Here's just kind of a video that's going to give you kind of a visual depiction of this speed advantage. It's all 3D animated, but it's useful for getting the picture. So here's the process here where you're seeing the spread and the print and the fuse. And if you look at comparing these technologies, you have an FDM system, which goes pretty slowly. You have to put down plastic and melt it in each location using that hot extruder. Laser sintering is a little bit faster. You have this powder bed, and you can draw on the surface. But again, here you have this area-based fusing system where each layer is independent of the amount of time you're printing. In addition to the technology advancements here, we're also trying to create less of just a 3D printer or a additive manufacturing system and more of an additive manufacturing environment. So not only do we produce the printer and its related software, utilities, tools to help you manage builds and fill build envelopes, we also have a detachable unit. What's nice here is that this door can open and you can have multiple of these build units. What that allows you to do is have the printer running with 100% uptime, assuming no no mechanical failures. You can run it all the time because essentially you can put a build in, print it, pull it out to let it cool in this processing station, remove the powder, and while you're doing that you can have another trolley ready to go that you put in, and while you're cooling the other build you can print this one. So you can always have the printer printing, you have full uptime because of the way this kind of ecosystem is designed. So one of the things I'll talk about is this open materials platform. What we're trying to do with HP's 3D print offering is basically open the market to multiple different powder suppliers and plastic suppliers to hopefully bring down the costs for the consumer. Basically, and we have many different polymer producers on board. Some of the largest chemical companies in the world, that's BASF's largest chemical company in the world, and Evonik and Arkema have produced megatons of plastic. I mean, huge amounts of plastic in the world. So we have a lot of the large players on board. And the plan here is to accelerate the expansion of the market and drive that 3D transformation I talked about earlier by making the materials and the technology available to as many people as we can by driving costs down as much as possible. The more we drive down cost, the more available this technology becomes, the more competitive it becomes with analog manufacturing techniques. So we want to drive reduction of powder and printing costs by getting as many large scale, large volume powder players as we can. And then additionally, down the road we have these voxel level capabilities, and I'll talk about this towards the end of the talk. To enable new technologies, new ways of producing parts that maybe weren't possible before. This open platform, it's not truly open in the sense that if you throw anything in the printer, you can easily break it, void your warranty, so on. But what we are developing is a certification system, a way for powder suppliers, any material provider to come in, test their printer, test their powder on a sample system, make sure that it works, and then sell that and move that directly into the market. So we have powder. Any powder manufacturer can potentially bring their material in, get it working, and get it through the system quickly. In addition to that, we develop HP branded powders. That's what's available right now with the existing system. And those are optimized specifically for operation with MJF. So we can't guarantee that you'll get amazing, perfect results with the certified powder, but the certified powder will provide a minimum level of quality. And it'll also allow us to provide a breadth of materials more quickly than through our branded pipeline, which takes time to optimize for those systems. So as I'm talking about here, the goal of this open platform is to bring down these barriers and advance widespread 3D printing adoption. Some of the examples of what we're doing, the plans for what we're producing, we want to address like kind of all angles of the market at once, both high performance materials, high cost materials, and then at the same time we also want to go down to commodity plastics. So what we have right now is this PA12, and this is kind of a rough timeline, but I'm not going to fix dates on any of these things, but you can see what we're working on. Nylon, elastomers, filled nylons, thermoplastics, commodity plastics, the kind of things that you would actually build. You know, the chairs you're sitting on right now are made out of those polyolefins that we eventually down the road want to get to. Okay, now we get to the really cool stuff. As I mentioned, I'm in R&D, so this is kind of the stuff that really excites me. The cool offering about MJF is that it allows us to deliver fluid to a particular point in the bed. What we refer to as voxels, essentially. You know, we have pixels in 2D, right, which are just XY squares. We now have voxels. We have XY squares plus a Z dimension that's related to the build thickness. But what we can do here is right now our system delivers fluids to the bed that allow us to do thermal control and a little bit of accuracy control. that's not all we can do with these fluids. As we develop systems with more available fluid slots and differently designed fluids, we potentially have the ability to modify materials on the fly and even create parts that have different material properties within the same part. And we can do that through a number of different processes, but the main two that are probably worth pointing out are you can dope materials in. So if you produce an agent that has a nanoparticle material, you can produce a composite on the fly. If you have, for instance, if you want to do your filled materials as long as the particle is able to be included in one of our 3D agents, you can actually produce the material with different material loadings depending on how many drops you put down, which can change the mechanical properties of the material, such as its tensile strength, its brittleness, its toughness, all sorts of different things. And then there also opens the possibility for us to design powders that can have specific reactions that are activated by dropping the agents onto that powder, which allows us to modify material properties as well. Some of the things that we're interested in examining, we're looking at color parts where you can produce cosmetic parts at or very near to the same mechanical properties as our mono parts that exist right now. Some of the other things that we can do potentially are producing conductive traces by dropping agents into the powder, which allows you to embed sensors into parts, or you could have strain gauges, all sorts of things. Rather than having to leave room in your design for putting conductive traces in, you can simply print them into the part, leave a spot for a chip on the part, plug the chip in at the end, and you suddenly have a functional part that can do some sort of electronic sensing, basically a smart part. Additionally, because of our background in 2D printing and security printing, we have a wide range of experience on how to do security printing. So you can produce watermarks that allow you to specifically track and trace parts. But additionally, one of the advantages of the third dimension is that we can potentially put those trackers inside the parts or places where they're not visible to the naked eye. So no one can find the tracker and decode it or something, but there'll be some sort of special system that allows you to observe the mark inside the part. And then one of the interesting things here is also using color as an indicator. If you're printing a gear, for instance, and you print a layer of color on the outside, and you know exactly what your tolerances are when that gear's teeth are going to start to fail, you can print a layer of color on the outside, and when that color leaves, when you suddenly have a part that, say, is pink, and it turns black, all of a sudden you're like, oh wait, I've got a gear that's failing. I'd better pull it out before my machine completely breaks and destroys something else down the line. So it'd be pretty useful to have parts that basically tell you when they're going to fail instead of just kind of failing and breaking everything on your process line. So I believe that pretty much hits the end of my talk. We're very excited about this technology. We're very excited about the promise we can bring. Our offerings are available at booth 427, which you can come visit over there, and we'll give you kind of a rundown on what our existing product offerings are, and I hope that gave you a flavor of what we're looking at in the future. So thanks for your attention, thanks for your time, and that concludes my talk.